Good afternoon, everyone. I am Siva and I am the project coordinator for our team. Today, I will begin my introducing the business background, the scope of our project, the main thing of interest, and high level overview of our conceptual model. Our database system is designed for a company operating in the retail logistic industry. The business manages product inventories, suppliers, customers, purchase orders, and sales. The company faced challenges in tracking suppliers' relationship, managing stock level, and generating insight from sales performance. Our database solutions aims to address these challenges in a structured and efficient way. The project scope includes three major components: developing enhanced entity relationship (EER) diagrams and UML models to capture the business data requirement, implementing a relational database in SQL based on this model, running SQL queries to demonstrate business use cases ranging from simple lookup to more complex subqueries. In assignment 1, our team identified key things of interest to the business. Number 1, product and their categories, price and stock quantities. Number 2, suppliers who provide this product. Number 3, customers who purchase product. Number 4, sales and purchase order who capture transaction. Number 5, order details which record the specific products sold in each other. These elements become the foundations of our data modeling.
Hi, it's me Sunil, and today I'll be presenting the ER diagram and UML diagram for our project on retail trade industry, focusing on logistic and supply chain management. That is the database designed for our project. First, let me talk about the ER diagram. The ER diagram is used to represent the database structure in our project. The main entities include supplier, products, warehouse, store, customer, purchase orders, sales orders, and their line items. The ER diagram shows how these entities are connected. For example, a supplier supplies many products. A customer can place multiple sales order, and each order is broken down into line items that reference specific products. We also applied generalization and specialization by grouping purchase orders and sales orders under a common entity called orders and combining warehouse and store under location. This helps avoid redundancy and ensures the database is properly normalized. Now moving to the UML diagram. The UML diagram takes the same entities but present them as classes with attributes and relationship. Each database table becomes a class and we can use multiplicity to show how many objects are related. For example, one supplier can be linked to many products. UML also emphasizes composition, which means that items such as PO line and purchase order line and sales order line cannot exist without their parent orders. At the same time, generalization is shown through inheritance, such as the common order class being specialized into purchase and sales orders. The UML diagram is especially important for moving from database design into software development, since it provides a blueprint for coding these entities as classes in a program. In conclusion, both diagrams describe the same system but from different perspectives. The ER diagram focuses on the data model and how entities relate in the database, while the UML diagram focuses on the object-oriented view showing classes, relationship, and dependencies.
Hey everyone, this is me, Shabda. My student ID is S374911, and today I'll walk you through how we transformed our enhanced entity relationship diagram to a practical relational model. This process involved a set of clear and systematic rules that converted our conceptual design to a logical database schema. The first and the most straightforward step was to map our strong entities like product, customer, and supplier. For every strong entity, we created our corresponding table. The attributes of the entity, such as product ID, name, and price, directly became the columns in that table. The entity's primary key, like product ID, became the primary key of the new table, ensuring that each of the record is unique. Next, we map the relationships. For a one-to-many relationship, like one customer placing many sales orders, we took the primary key from the one side, that is the customer ID, and added it as the foreign key in the table on the many side, which is the sales order table. And for the many-to-many relationship, such as one supplier providing many products, we created a new junction table that is the product supplier. This new table holds the primary keys from both the supplier and product tables as foreign keys, linking them together. Well, then we moved on to our weak entities like a PO line that just cannot exist without a purchase order. So they were also given their own table. We included a foreign key that linked them back to the primary key of its owner, like purchase order. Then finally, for our ISA hierarchies, like a location that was either a warehouse or a store, we used the superclass and subclass strategy. We created a table for the parent entity, that is location, and then separated the tables for warehouse and store, with each subclass table containing a foreign key that referenced back to the location table.
Hello everyone, my name is Rohan and I was responsible for implementing our conceptual models into a working relational database using SQLite. My role involved creating all the tables, inserting synthetic but realistic data, and then developing and testing 4 SQL queries that demonstrate different levels of complexity. We structured the database with key entities such as suppliers, products, warehouses, stores, customers, purchase orders, and sales orders. To make sure that the schema was robust, we enforced primary keys, foreign keys, and unique constraints, and we populated the tables with sample data that reflects real-world logistics and retail transactions. One of the queries I'll show is our moderately complex query. This query uses an outer join to combine suppliers, purchase orders, and purchase order lines, and then aggregates the results. The purpose is to calculate the total purchase order value for each supplier. The next query I'll highlight is our complex one. It uses a nested subquery with aggregate functions to identify the top-selling products by total quantity sold. The database calculates total sales for each product and then selects the maximum. As you can see in the result, modern query 3 output, we get results such as global traders with a total of 9,200, Tech Source Limited with 20,400, and Elite Electronics with 5,200. This is useful for management because it clearly shows suppliers spend and can highlight which suppliers account for the highest procurement costs. Also, in result complex query for output, we see that the top selling product is the DEX lamp. This insight can be applied in inventory and marketing decisions, for example, prioritizing restock or running targeted promotions for high demand products.